and welcome to this tutorial on strong acid, strong base titrations. We're going to be talking about a few things such as a list of strong acids, strong bases that you need to know. In addition, we're going to go over some of the stages of a titration in general. Then we're going to work a couple of examples here. Alright, so let's go over the strong acids, strong bases. First of all, you're supposed to know the list, at least half of them that are on here. This will help you to determine whether you're dealing with a strong acid, strong base titration or a weak acid, weak strong base titration. It depends on what type of titration you're dealing with, but at least if you know what's the species that you're interested in, if they're strong or weak, then you're able to determine what kind of methodology to use. So here you have strong acids. These are your list of strong acids here. And then you have your strong bases. Generally for the strong bases, you have these groups here are generally going to be group 1 and group 2 hydroxides, and those are going to be your very, very strong bases, group 1 and group 2. For the strong acids, I just recommend knowing just a few of them. For example, hydrochloric acid, that's a very strong acid. Stomach acid, you know that's strong. That'll help you know that. Sulfuric acid, battery acid, things like that. That'll help you. Usually the halides, like the bromine, and iodine, those halogens, and chlorine is also a halogen. You should just know that those will be strong acids: chlorine, bromine, iodine. But however, fluorine, HF, would be a weaker acid, so this would not be in the list. So the only halogen really that's not on here is this one and then the very bottom one. But the ones in the middle are just perfectly fine. And then your chlorates, so your perchloric acid and your chloric acid. Anything below that is not very strong. Okay. Then your next one, you want to know about the stages of the titration. So basically, before you want to know, the first stage is before you add any titrant or whatever it might be. So in this case, we're doing strong acid, strong base. So you're going to start out with a strong acid and you're going to add in strong base. So this titrant in this case would be your strong base. Before the equivalence point is also a stage. Okay, and then we're going to learn how to deal with all of these stages once we do a problem in detail. Your third stage is the equivalence point. Once you reached it, remember your equivalence point is the point where your moles of acid is equal to your moles of base. So basically they perfectly neutralize each other, and the equivalence point for a strong acid, strong base titration, generally the pH is going to be 7 because they fully neutralize each other. Remember the definition of a strong acid, strong base. Strong acid, strong base, let's go back to the list here. For example, with hydrogen chloride, if you were to write it out, that just means that it dissociates completely. It breaks up completely into hydrogen ions and chloride ions. Okay? With weak acids, so let's say you had a weak acid like HF, like we were saying earlier, that is going to have an equilibrium condition because it doesn't break up fully. In addition, it only partially breaks up into hydrogen ions and fluoride ions. It doesn't break up 100%. So if you have 1 molar of this, you're not necessarily going to have 1 molar of this and 1 molar of this. There's going to be in different amounts. If you had 1 molar of HCl, then you're definitely going to have 1 molar of that and 1 molar of chloride. So I just wanted to clarify that. Now, so therefore, since it breaks up completely, all of the hydrogen ions react with all of the water, or with all of the base, sorry, and gives you water, and water has a pH of 7. And then beyond the equivalence point, you're obviously going to go past the neutral point, and if you're adding base, you're going to become basic. All right, so let's work this first example here. So we have 40 milliliter volume of HCl is titrated with 0.1 molar NaOH. They want to know the pH before the addition of base, after the addition of 10 milliliters of base at the equivalence point, and after addition of 60 milliliters of base. Now, for this here, you need to first of all convert this to liters. So you're going to move the decimal place three places. So that's 0.04 liters. That's the first thing. Okay, and then one of the first things that you want to do, let's go to another page here. So let's rewrite this detail here. Oops. So let's rewrite this. So we have 0.04 liters of a 0.100 molar solution of HCl. Remember that 0.01, this is equal to, remember that molar solution means moles per liter. So you're going to have 0.100 moles of that per liter, per 1 liter solution. Okay? So essentially what you want to do is you want to find out how many moles of HCl you have. So we're going to do this. Liters cancel out. Leaves you with 0.004 moles. Okay. So we have 0.004 moles of HCl. Now they want to find the initial pH, but before we do that, let's determine how to find the equivalence point. How do we find the equivalence point? Remember, the equivalence point is when the moles of acid equals moles of base, right? So if we have this amount of acid, right, then we're going to have an equal amount of base. So that means the amount of base that we have is 0.004 moles. So therefore, what we can say, we know the base, and we also know the concentration of the base. The concentration of the base, let's go back here. Concentration of the base is 0.100 as well. Sodium hydroxide is your base. So therefore, we're going to say we have 0.004 moles, and we have, for every 1 liter, we have 0.100 moles of base, right, or OH minus. That now the moles cancel out. That leaves us with liters. So that tells us how many liters of base we need to add in order to reach the equivalence point. So in this case, 0.004 divided by 0.1 should be 0.04, which is basically 40 milliliters. Okay, so our equivalence point is when we add 40 milliliters of base. Okay, so we'll just keep that in mind when we do these problems. All right. So now, therefore, let's go ahead and do part A here. So they want the pH initial. So they want the initial pH. Let's go ahead and do the initial pH. So remember, we said that HCl breaks into hydrogen ions and chloride ions completely because it's a very strong acid. It's one of the acids in the list. Therefore, if we have 0.100 molar of this, of HCl, right, then that means we have 0.00 molar of this and 0.100 molar of this, because it breaks up and you have 0.1 of each. Therefore, we can say we're going to calculate the pH here. pH is going to equal negative log of hydrogen ions, and we already know what the hydrogen ions are. Alright, when you do that, you're going to get a pH of 1.00, or just 1. Alright, so that's your answer for part A. Alright, so that's part A. Let's go ahead and just delete that real quick just to give us more room. Alright. Okay, so now let's go ahead and do part B. Part B is before addition or after addition of 10 milliliters of base. So now we have 10 milliliters, which is 0.01 liters. Okay, so we added that much base, and the solution is 0.100 moles per liter. Okay, I'm just going to write OH minus because sodium hydroxide breaks into sodium ion and hydroxide. And hydroxide is really what you're looking for. So liters cancel out. That leaves you with 0.001 moles. Okay. Now what we want to do is we want to do an IAF table. Okay, so let's go ahead and do an IAF table. So we're going to have I stands for initial, and then A stands for addition, like what happens if you add, what happens, or you could call it after, like whatever happens, and then the final. So you have. So what is the reaction? The reaction is HCl plus sodium hydroxide gives you H2O and NaCl, correct? So that's your reaction. What is the net reaction? The net reaction is just the Cl and the sodium. Those are spectator ions. Those don't participate in the reaction. The only thing that participates in the reaction is hydrogen ion and OH minus. So we're just going to focus on those. Those are the only things that we really need. Alright, with water, you don't have to worry about water whenever you do the IAF table. Water is trivial. You don't have to worry about it. With hydrogen ions, what did we start out with? Well, we started out with 0.004 moles. We calculated that earlier. You want to do these in moles, okay? So moles. Hydroxide ion, we just calculated that. That's 0.001. And then what happens is the hydroxide ion is going to react with hydrogen ion. So therefore, this gets consumed and this gets consumed, right? Because this reacts to form water. So therefore, you're left with 0.003 and 0. So those are your final amounts. So therefore, you have 0.003 moles of hydrogen ion left. Now you need to calculate the hydrogen ion concentration. So you take the moles and you divide it by the volume. Well, what is the volume? The volume is the initial volume of 0.04 liters plus 0.01 liters of base that you added. So a total of 0.05 liters. Okay, so we're going to go back here, and this is going to be 0.05 liters. Then when we do that, we're going to get 0.06 molar. Then we're going to go ahead and calculate the pH now, which is the negative log of 0.06. And that's going to give us a pH of roughly 1.22. Okay? So that will be part B. Okay. So that's part B. Let's go ahead and go ahead and just delete this real quick. Alright, delete that. Alright, we're going to go ahead and do part C now. So part C was at the equivalence point and then determine the equivalence volume, which we did. We determined the equivalence point, right? That was when you add 40 milliliters of sodium hydroxide, right? So we determined that earlier. Convert that to 0.04 liters and multiply by the concentration, 0.100 moles per liter, and you're going to get the 0.004 moles. Okay? So that makes sense. There's no IAF table. You don't really have to do an IAF table. You could. If you did, you'd find out that you get 0 of both. So you're gonna get a final for both of these guys, hydrogen ion and hydroxide. You're gonna get a final of 0 for both of them because they fully neutralize. Okay, so what do we do? Well, since they fully neutralized, they only made water. So what's gonna happen with water? Then the pH of water is 7. So therefore, the pH of this guy, this solution should be 7. So that would be your answer. They fully neutralize, and then you end up having a pH of water, which is 7. So this one's pretty easy. And then D, after addition of 60 milliliters of base. So let's go ahead and do that. So 60 milliliters of base. All right. That's 0.06 liters times your 0.100 moles per liter of hydroxide. Gives you 0.006 moles, which is greater than the 0.004, if you recall. We could do an IAF table, so let's go ahead and just do that real quick. Oops, that should be hydroxide. Alright. Don't have to worry about water. Alright, so we started out with 0.004 here. We started out with 0.006, right, that they gave us here. So what happens? Well, this can't fully react with this, right, because there's only 0.004 of this. So therefore, only 0.004 of this gets to react. And we have 0 hydrogen ion, and then we have 0.002 moles of this left. So therefore, we have this much left. So we're going to say that we have 0.002 moles of hydroxide left. We got to convert it to a concentration, right? So let's go ahead and convert that to a concentration. So that divided by the volume. What was the volume? It was 0.04 liters, I believe. Yeah, 0.04 liters that we started out with, plus 0.06 liters, right? Which is a total of 0.10 liters, okay? So we're going to divide this by 0.10 liters, and that gives us a concentration of should be 0.02 molar. Okay. So now that we got the molarity or the concentration, let's go ahead. Well, we can't calculate the pH from this directly. We're going to have to calculate the pOH. Right. So pOH equals negative log of hydroxide, which is the negative log of this number. That's going to give you a pOH of 1.70. Then you can calculate the pH because using the formula pH plus pOH equals 14. Okay? So then now that we know the pOH, then pH is equal to 14 minus pOH. Alright, so that's the formula you want to look at. So we're going to do 14 minus our 1.70, which gives us a pH of 12.30. Okay? And that's how you do it. That's the last part of the problem. Alright, let's go to another example here. Consider the titration of 25 milliliters. Let's convert that to that. Of that much HCl with that much base. So this is a strong base. That's a group 1 base. And this is a strong acid. So this is strong acid, strong base. Calculate the pH after the addition of each of the following volumes of base. Okay? So let's go ahead and do that. So we're going to do the initial pH. So part A is the initial. Okay, where we add no base at all, right? We just find the concentration of that. That's pretty easy. Well, remember that we said that that breaks up into hydrogen ion and chloride. So whatever the concentration is here, that's going to be the concentration of this guy, right? So therefore, we could just take the negative log of 0.125 and get our pH. In this case, our pH will be roughly 0.90. Okay, so that would be the answer for part A. And then for part B, let's go ahead. Well, hopefully we have enough room. Part B, that's going to be 0.003 liters of base, right? So let's find out how many moles we have. Well, we have a concentration of 0.100 moles of OH minus. That's over here per liter. Liters cancel. Leaves you with it's going to be very small, 0.0003 moles. and let's find out how much acid we have, right? So we had the 0.025 liters that we added, that we have initially, times the 0.125 moles of acid, 8 hydrogen ions, or HCl, per liter. And that gives us 0.003125 moles. Okay. We're going to go to another page here. So let's do an IAF table here. So we have hydrogen ion and OH minus yield water. Okay, so we have initially we have 0.003125 there, 0.0003. So basically all of this is going to react with this here, so we're going to subtract that off. Okay, when we do the math, that's going to be 0, and this is going to be 0.002825. Okay, so now we have this much hydrogen ions left. We can go ahead and do the pH now. So let's first find the hydrogen ion concentration. So hydrogen ion concentration equals the amount here. Remember, these are in moles. Divided by the total volume. So what's the total volume? We started out with 0.025, and we added 0.003, right? So 0.025 plus so let's go ahead and add that. So we started out with 0.025, and we added 0.003. That gives us 0.028 liters. Okay, so we're going to take that and divide that by that volume. Okay. Go ahead and do that calculation. Calculator real quick. 0.028, or yeah, 0.002825 divided by 0.028. Okay, so we get about approximately. It kind of makes sense. So about 0.1. I'm going to write out the decimals here, and then we're going to go ahead and just do the pH. Just a negative log of that number. Approximately. So we're going to do the log of that. Go ahead and do it out here real quick. Sorry about that. Let's go ahead and calculate this. It's going to be alright, so about -1, roughly. Okay, let's go ahead and put that away. Alright, so the value is about -1. So we're just going to round it to -1. Oh, I'm sorry, -1, +1. Okay, so we got +1 for the pH. The next part is when we add 20 milliliters. So let's go ahead and do that. Okay. Alright, so let's go to part C. What was part C? So we're adding 20. Convert that to liters. Alright, so we're going to multiply that by the concentration. And that gives us 0.002 moles of OH minus. Okay, so that's how much base we have. Again, IAF. So this remained the same, like last time, 3125. Again, if you look at this, we still have less moles of this than hydrogen ions. Therefore, we're not really at our equivalence point yet. Okay, so we're only at our equivalence point when this is equal to this. So we're going to subtract that off. So that is 0, and this will be 2.5. All right. So therefore, we're going to go ahead and take that hydrogen ion, convert it to a concentration. The total volume is should be 0.09 if I'm not mistaken. So 0.025 plus, oh, I'm sorry, 0.025 plus 0.02, so 0.045. Okay, so let's go ahead and calculate that real quick. Okay, so you got 0.025. So let's go ahead and write that out here. Let's bring that back up. All right. All right. Let's go ahead and do the log of that now. So 0.025 and then the log of that. So it's about 1.6. So the pH is about 1.6. Okay, and that's part C. Not too bad. And then we're going at part D, which is 65 milliliters, which is 0.065. Again, convert that to moles using the concentration of base. And you get 0.0065 moles of OH minus. So far so good, it's pretty easy. So you have your IAF here, same idea. Sorry, this is going a little slow. So you have 0.003125. You have 0.0065. But notice here, you already passed your equivalence point. Because now you have 0.0065 of this, 0.003125 of this. So you already passed it. Therefore, not all the OH minus is going to react. So only 0.003125 is going to react with this. So this is going to fully neutralize. That's going to become 0. And this number down here is that. That's your moles. Now, therefore, you only have a hydroxide. So we had to find the concentration of hydroxide. Divided by the total volume. In this case, 0.065 plus 0.025 gives us 0.09 liters. So we're going to divide that by 0.09 liters. Okay, clear that out. Okay, So 0.0375, and let's just go ahead and do the log that right away. All right, so we got a pH about 1.4, or pOH rather, of 1.443. We'll round it. So we have a pOH of about 1.43. Therefore, we get a pH of 14 minus that, which is 12.57. So you see how once we pass the equivalence point, it goes rapidly basic, because now we have pure OH minus in the solution. So now it's a pure basic solution. And that's all there is to it. I hope you found this useful. Thank you. Have a good day.